The product rule. Here it is. If y equals uv, where u and v are both functions of x, that is, y is the product of two other functions here, then we can say the derivative of y, dy by dx, equals v du dx plus u dv dx. You've got to learn this rule. Not only learn it, but identify when you can use it. So let's have a few examples of it in practice. Here's example 1. Differentiate the expression y equals x squared minus 3 multiplied by the square of x plus 1. Here we have the product of two functions, one of them being x squared minus 3 and the other being the square of x plus 1. So the first thing we do here is identify the type of rule that we're going to need to differentiate it. In this case, the product rule, because it's the product of two functions. So we say let u equal x squared minus 3. That's the first function here. And similarly, v equal the other function, in this case the square of x plus 1. And now I'm going to work out, because let's just write down the product rule on this page. So we've got dy by dx equals v du dx plus u dv dx. So we need these terms here. Well, we've got u and we've got v. Let's find du by dx is 2x. That's the derivative of what's inside the brackets. Here, dv by dx, well, we're going to need the chain rule to differentiate this. So we bring the power down, that's 2. Got what's in the brackets still. We take 1 off the power, multiply by the derivative of x plus 1, which is 1. So this is what we're left with. Therefore, we can say that dy by dx, using this here, equals v, that's x plus 1 all squared, du dx, which is 2x, I'm going to squeeze that in the front there to make it look a bit nicer, plus u, x squared minus 3, dv dx, which is 2x plus 1. Now I'm just going to tidy this up. So dy by dx equals, well, I'm going to tidy this up by looking for common factors. Well, what have we got? Well, 2 is a common factor of both of these terms here. What else? We've got x plus 1 here, and here we've got x plus 1 multiplied by x plus 1. So x plus 1 is a common factor of both of these terms. So let's take out the common factor, 2x plus 1. So what am I left with? Well, I'm just going to use a different colour so we can see, hopefully a bit easier, what we've got here. So 2x plus 1 taken out as a factor of this leaves me with x and an x plus 1 plus. Now if I take 2x plus 1 out of here, I'm going to lose these two bits. So I'm just left with x squared minus 3. So should we check that? 2x plus 1 multiplied by x plus 1 gives us 2x x plus 1 squared. Brilliant. And 2x plus 1 multiplied by x squared minus 3 gives us 2x plus 1 multiplied by x squared minus 3. Sorted. Well, let's tidy this up then. See if we can factorize the whole thing here. So we're going to do 2x plus 1, tidy up what's inside the brackets. X squared here plus x squared gives us 2x squared. We've got an x here, and then we've got a minus 3. Great. Last line, I think I'm going to try and factorize this fully. I can see this. This is going to factorize nicely. So I've got 2x plus 1, 2x plus 3, and x minus 1. This is my final answer. Example 2. Differentiate y equals the cube of x squared plus 1 and the square multiplied by the square of x cubed plus 1. Here we have the product again of two functions. So we can say this, let y equal uv. And the u I'm going to call this bit, and the v I'm going to call this bit. Let u equal the cube of x squared plus 1, and v equal the square of x cubed plus 1. And if we just recall the product rule, dy by dx equals v du dx plus u dv dx. You've got to learn that off by heart. It's not given in the formula booklet. So let's differentiate these terms. And we're going to differentiate these using the chain rule. So we bring the power down, 3, got the brackets, x squared plus 1, take 1 off the power, and then I need to multiply it by the derivative of what's inside the brackets. So I need to multiply this by 2x. In this one, dv by dx, I'm going to take the power down, write in what's in the brackets, take 1 off the power, and then multiply it by the derivative of what's in the brackets. That's 3x squared. See, we need to become proficient at using the chain rule to make this process much quicker. So using this, I can say, using the product rule, I can say, therefore, dy by dx equals v, here it is, x cubed plus 1 squared, du dx, I've got to all of this squeeze in, 3 multiplied by 2x is 6x, and then here, of course, I've got an x squared plus 1 squared. Continuing with the product rule, I'm going to add u, which is x squared plus 1 cubed, and multiply that by dv dx, which is over here. 2 multiplied by 3x squared is 6x squared, and then I've got an x cubed plus 1 here as well. Now we're going to try and tidy this up by looking for common factors. Let's have a look here. Well, I've got a 6x here and a 6x squared here. So this is 6x times x. So 6x is a common factor. I've got an x cubed plus 1 here, multiplied by x cubed plus 1, and an x cubed plus 1 here. So that's a common factor. I'm going to start writing these down. So 6x is a common factor. X cubed plus 1 is a common factor. Any others? Yeah, look at this one here. X squared plus 1 squared is a factor here, because x squared plus 1 cubed is the same as x squared plus 1 squared multiplied by x squared plus 1. So I'm going to take this out as a factor, x squared plus 1 squared. I'm going to use a purple brackets again so we can track what's going on a bit easier. So if this is the factor that's taken out, all we're left with here is x cubed plus 1. And similarly, if we take all of this out on this side, we are left with x from this 6x squared term here, and we're left with x squared plus 1 from this here. Let's tidy this up. 6x x cubed plus 1, x squared plus 1 all squared. And then in my purple brackets, I've got x cubed plus another x cubed. So that's going to give me 2x cubed. And then here I've got a plus x. And here I've got a plus 1. Now this bit doesn't factorise. So this is my final answer. Example 3. Find the x-coordinates of the stationary points of the curve y equals the product of x squared minus 1 and root 1 plus x. Well, to find a stationary point, we first work out the gradient function and then let that equal 0, because the gradient of the tangent at a stationary point is always horizontal, and therefore the gradient is 0. So we need the gradient function. That is the derivative of this function here. How are we going to do that? Well, this is the product of two functions, so we're going to use the product rule. dy by dx equals v du dx plus u dv dx. Got to learn this off by heart. So here I'm going to say let u equal x squared minus 1 and let v equal the root of 1 plus x. I don't like it like that, so I'm going to write it as 1 plus x all to the power of a half, because a root or a square root is equal to a half. Looking at this first one, du by dx is 2x, and in this second one, dv by dx, using the chain rule, becomes a half, multiplied by the brackets, take 1 off the power, multiply it by the derivative of what's in the brackets, in this case 1, so we multiply it by 1, so it stays the same. So now I can say that du by dx equals v, that's 1 plus x to the half, multiplied by du dx, which is 2x, plus u, which is x squared minus 1, multiplied by dv dx, which is a half, 1 plus x to the minus a half. Well, I'm going to let this equal 0 to find the values of x at the stationary point, because the gradient at the stationary point is 0. To make it easier for myself, though, I'm going to try and tidy this up by looking for factors and rearranging it and so on and so on. So actually I can write this as 2x plus 1 multiplied by the 2x that I've got here, plus x squared minus 1 all over 2 lots of x plus 1 to the half. Well, this bit is quite straightforward, quite self-explanatory, because this x squared minus 1 over 2 brackets x plus 1 to the half is the same as this, obviously. Whereas here it's a little bit trickier to work out. So if we divide by x plus 1 to the half, we end up with x plus 1 to the 1. That's where that comes from. And because we've got a half here, we've got to double the top to make sure that it has the same value as the original. Right, now what's the next move going to be? Now we've got x plus 1 as a common factor here, because here we've got the difference of 2 squares. So this bit here is equal to x plus 1 and x minus 1. So I can take x plus 1 out as a factor on this numerator. And if I do that, I'll get my 2 times the 2x here, so that's 4x, x plus 1, plus x plus 1, x minus 1, all over, and this is the same, 2x plus 1 to the half. I'm going to write that line out first and then take the factor out. I think it'll be a bit easier to follow then. So this is where we're at. Oh, I'll squeeze it in here. So now I'm going to say x plus 1 is my factor, so take that out, x plus 1 here. And if I take that out as a factor, I'm left with 4x from this term, and I'm left with plus x minus 1 in this term. And of course, it's still over the same thing. That is 2x plus 1 to the half. Now if I tidy this up here, this bit here is 4x plus x, so that's 5x, and then we've just got minus 1. And then to finish, so I've got x plus 1 multiplied by 5x minus 1, and I've got 2x plus 1 to the half. To finish, if I divide throughout by this one, I can then back on the top here, write x plus 1 to the half. So I'm going to do that on a new sheet of paper. Try and keep that one on the screen there for you. Here we go. So dy by dx equals a half from this bit here, multiplied by the 5x minus 1, multiplied by x plus 1 to the half, because x plus 1 to the power of 1 divided by x plus 1 to the half is the same as subtracting the powers. So that's where this one comes from here. Now this is much easier for me to say, right, okay, now I'm going to let dy by dx equals 0. So all of this is 0. A half 5x minus 1 x plus 1 to the half equals 0. So for these to equal 0, there are two possible values for x. Either 5x minus 1 equals 0, which implies that x equals a fifth, or x plus 1 equals 0, which implies that x equals minus 1. So those are the x coordinates of the stationary points of the original curve.